Alright, welcome to a little mini lecture here on the law of cosines. Alright, let's jump right into it and start off with a quick question. Here is this wonderful triangle right here. Can you tell me what C equals? Alright, well, if we look a little bit more closely at the triangle in question, so I've got a side of 3, a side of 4, and C is what I'm trying to figure out. And somebody put a little square right here, letting me know that I'm dealing with a right triangle, and of course the all-time classic, the first math theorem even, the Pythagorean theorem, tells us that, alright, well, to get the hypotenuse in a right triangle, it's the sum of the sides squared, and the hypotenuse squared is equal to that, so we've got 3 squared plus 4 squared is equal to C squared. Alright, and then we can compute that, 9 plus 16, and there we go. Oh, look, somebody made sure we got a square here, so we've got C squared is equal to 25. And because we're dealing with a length here, C's got to be positive, so C has to be the square root of 25, which we already let slip, is equal to 5. Great. Hey, there we go. Nice, easy, quick question. Right, and maybe you were a little bit more eagle-eyed. You might have immediately seen, ooh, this is a very famous Pythagorean triple, 3, 4, 5. Some other fun ones, 5, 12, 13, and you can generate them. There's infinitely many of them, even. All right, so if you saw that immediately, good on you. If you went through the whole calculation like I did, pretty good. All right, so that went great. Perfect. All right, well, what's next? Well, what about this triangle? All right, so things are a lot different now. Obviously, the triangle visually looks different. Even though I still have my 3, I still got my 4, and I still have my C. So I'm still trying to figure out C based on what 3 and 4 are. But it seems like we're probably going to need a little bit more information about this triangle. Right before, we had a right triangle, and we know something about right triangles, right? We know the measurement of that right angle, right? It's 90 degrees, or pi over 2 radians. So we're in this situation where I have two sides and a side I'm trying to find, but before I had two sides and an angle. And note it was an angle that was pointed at the side. We didn't know. Alright, so I probably need some knowledge of this angle right here. My cursor is going around. Alright, so let's say somebody did come in and give me the measurement here and said, hey, that's 32 degrees. Obviously, this triangle is very much not the scale, but that's fine. Alright, well, bad news, doesn't seem like you can use the Pythagorean theorem, right? The Pythagorean theorem says you need a right angle, and 32 degrees ain't it. So, what do we do? Can't use our wonderful theorem here. Or can we? Alright, so let's investigate this image a little more carefully. Okay. Alright, so what did I do here? I put a dotted line going from this top tip here of the triangle, going all the way down, and note it's hitting it perpendicularly, so we'll have nice right angles on both sides here. So I actually have two right triangles now, so I kind of took my one triangle and broke it up into two right ones. Alright, well, to use the Pythagorean theorem, I need to know this length, and then, well, now I have two different bottom lengths down here. Alright, well, let's introduce some symbols. So let's call this dotted line's length h. Okay. And let's call this length from here to here, so this part of the triangle on the right, let's call that x. So x is measuring the length from the dotted line here, from the left to the right. Okay. Well, if this length here now, we're calling that x, and the whole thing is 3, that means this length over here will be 3 minus x. All right. Right, because no, when I add these two together, I'll get 3, and that is the original length. Alright, so now I have two right triangles, and I now have symbols for all of their sides. So by the Pythagorean theorem, I can go ahead and get relationships between all of my quantities here. Right, C is the hypotenuse for the triangle of H, and 3 minus x is the sides. So Pythagorean theorem says, there we go. Alright. And here, my 4, h, and x are going to give me this relationship. Alright, so there we go. Now what? Alright, well, this is just asking to get squared out, so let's go ahead and expand this term right here. That will give us this. Right, we'll get the 3 squared, and we'll pick up twice 3 times x. Note it'll be negative, because of the minus, and then we'll pick up an x squared. Now, after we've expanded this, that's that term right there, hey, the h pairs up with this, and, oh, when you know it, that's what 4 squared is. So we can go ahead and plug that in, and that gives me this wonderful little expression right here. No, we've got c squared, we got 3 squared, we got 4 squared. Hey, that's pretty close to the Pythagorean theorem, but we have a kind of a little extra bit here. All right, well, now let's go ahead and move that around. So we kind of have something that looks almost like the Pythagorean theorem, where we have this sort of a defect term hanging out right here. All right, well, I know 3, I know 4. C is what I'm trying to find. I know 2, I know 3. But x, right, well, I don't know what that is. Right, it's just whatever this length ended up being, but I don't know what that is. So how are we going to deal with that? Right, and generally, like, well, it'd be great if I could get rid of it. Right, because I know everything else, but x is sort of this mystery length, and how do I deal with this? All right, well, as I kind of already gave away here in the title, and also just the general theme for this, the law of cosines, it's probably time for some trig to show up. And let's think about what I have here. I've got this angle, and I don't know h, and I don't know x, but I do know 4. And the x is what I'm trying to get rid of in the equation. I've already gotten rid of the h. So I get rid of the x. Well, that's the adjacent and the hypotenuse of this angle, and wouldn't you know it, that's what cosine gives me. Cosine of an angle will give me the adjacent over the hypotenuse. All right, so in our situation then, we've got cosine of 32 degrees has to equal x over 4. That's the adjacent side, and that is the hypotenuse of my right triangle. All right, and so then I can solve for x and plug that in. And all right, now we're off to the races because we've solved for x, we've removed it from the equation, and c is what we're looking to solve. So let's do it. All right, we've now worked out the following equation based on my triangle. I split it into 2, applied the Pythagorean theorem twice, and pulled in cosine to help me out. And then now some pretty straightforward calculations. We square that, multiply all of that out. All right, that cleans up to 25, and now we can keep this in a nice closed form. Take the square root of both sides, and there we go. I have solved C. I have a closed form solution. It's the square root of 25 minus 24 cosine of 32 degrees. And now note, I know this is a positive quantity because cosine never gets any bigger than 1, and so this at most could possibly equal 1. So I know it's going to be positive, so I can take the square root of it, no problem. All right. Now, for the decimal enthusiasts, you can go ahead and get a good approximation of this using your favorite calculating equipment. And I've gone ahead and done that. I got that C is roughly 2.156. And again, note, not to scale in the picture. All right. Hey, beautiful. We did it. All right, a little bit more involved than just applying the a squared plus b squared equals c squared. And in fact, this always works. So there's nothing special about 3 or 4 or 32 degrees in that wonderful little problem we just worked out the details of, because I can always pull that maneuver where I draw my height of my triangle here and split the bottom's length into a minus x and x, and then we can derive the titular result of the law of cosines. C squared is equal to a squared plus b squared minus this extra piece here, this 2ab cosine of c, and why it ends up equaling this, well, we just worked out the details why that goes down. Great. All right, so let's note a couple of things about this shiny new formula before we go ahead and apply it on a new problem. So when C is a right angle, 90 degrees or pi over 2 radians, then the angle, cosine of that angle is 0, and so you'll get your C squared is equal to A squared plus B squared. So it's just a Pythagorean theorem. So this result here is basically just the superpowered version, right? Before, you're only allowed to use that for any right triangle, and here we're able to use it for any triangle now with any angle C there. And furthermore, if we were to label the angles A and B here, you can get similar equations as well. You can do the exact same derivation. There was nothing special about A, B, C, or the angle C where they were located. You can have the sides and the angles located anywhere and get the same results. Okay. Great, well now that I've got a wonderful shiny new equation, let's give it a spin on some fun problems. Okay, so let's do another one. Alright, so here we go. We have a side, an angle in between them, and I want to figure out the angle, the length of the side facing away from the angle. Alright, we'll pop it into the equation. X squared has to be this side squared plus this side squared minus twice the product of the sides and cosine of the angle. All right, and cosine of pi over 3 is one of the nice ones. Gets me a value of 1/2, and so we square it all out, and if you clean up all those computations there, you can verify that indeed you get 7. Pretty cool. And then we can take the square root and get that x is equal to 7, and again, for the decimal fans, that's approximately equal to that. All right, good stuff, right? Okay, well, let me pull a sneaky on you. Let's say, now that I know that this side here is equal to square root of 7, what if I wanted to figure out this angle alpha right here? Well, I clearly know this angle, I was told that, but can I figure this one out? The answer is yes, I can, because I can apply the law of cosines again, but now using 2 and square root of 7 as my sides, and 3 as my opposite side of the angle in question. And now I have this equation, which has one unknown, and if I go ahead and clean up my numbers, like so squaring them out like that, I can move some things around and isolate my cosine of alpha. And furthermore, we can then take the inverse cosine, or the arc cosine of all sides, and get that, hey, here's what alpha needs to equal. It's 1 over 2 root 7, the arc cosine of that. Hey, good stuff. Cool, so that's pretty exciting. So here we see that you can actually use the law of cosines not only to compute sides of a triangle, but you can actually use them to figure out angles as well, right? Because it's part of the equation as well. And note that's a lot stronger than the Pythagorean theorem. Pythagorean theorem just gave me a squared plus b squared is c equals c squared. Well, now I can compute some angles with law of cosines. And again, for the decimal enthusiasts, you can go ahead and again, an approximation for this. It's 1.38 radians, and if you want it in degrees, it's 79.11, approximately, not explicitly. All right, I got one more problem for you. And oh boy, it's everyone's favorite, a word problem. And I take no credit for this word problem. This is one that one of my old friends wrote, and let's take a minute to read it. 2 planes leave an airport at the same time, each flying 110 miles per hour. One flies at a bearing of north 60 degrees east, and the other flies at a bearing of south 40 degrees east. How far apart are they after 3 hours? All right. Well, I'd like you to go ahead and pause the video and try to work this one out on your own. And when you've got that done, come back and we'll work through the details here. All right. So hopefully it went well for you. Hopefully you looked up what this means exactly, which is part of why I love this problem that my buddy wrote. I had to look that up. I'm like, what does this notation mean? But it's pretty easy to read. So if you go ahead and draw some axes with north, east, south, and west, this is just telling you, all right, start north and go 60 degrees towards east, which would be that. And since we're flying at 110 miles per hour, after 3 hours, we're at 330 is the length there. All right, and then similarly, you start south, go 40 degrees east, like that. And again, they're flying at the same rate, and we want to know how far apart they are at 3 hours. And how far apart they are would be the length of that right there, which is what we're looking to solve for now. And note that in between, hey, I can compute that that's got to be 80 degrees, and wouldn't you know it, I now have a beautiful law of cosines problem to work the details out of. All right, so by the law of cosines, we know that x squared has to be the sum of those sides squared minus twice their product times cosine of the angle. All right, and in this one here, I want to do a little more algebra manipulations. So note I'll have two 330s quantity squared, and note I've also got, hey, two 330s quantity squared. I can then factor those out, and now when I go ahead and take the square root of all sides, I'll get something like this, and by properties of square roots, I know that those break up multiplicatively like that, and hey, this 330 squared goes away. Right, so again, this is good practice, keeping everything in nice closed form. Good stuff. And as always, for the decimal enjoyer, if you want to get an approximation of what x is equal to, there it is. Beautiful. All right, good stuff. All right, and hopefully your work matched mine. Oh, one of us is right. Hopefully it's me. All right, and let's go ahead and recap everything we just talked about. So, big takeaway, if you've got this wonderful triangle situation right here, there are three formulas you can derive out of these, and they are collectively known as the law of cosines. Right, and so note this one right here, most similar to the classic Pythagorean theorem, and life is pretty good. All right, so there you go. Thanks for joining me with this little mini lecture on the law of cosines, and I'll see you next time.